In today's video lesson, we are going to learn about gas laws. In today's video, it is roughly 19 minutes long, but I will let you know that 12 minutes of that is a video explanation of how to solve 4 different gas law problems. When we get to the example problems, I'm going to ask that you pause the video, try to solve them on your own, and then if you need help, watch the video explanation. To check your answers, just skip ahead a couple minutes until the answer is shown for that video problem. If you got it correct, awesome, continue on to the next one. If you got it wrong, then I'm going to ask that you rewind the video a little bit and watch the explanation for a little bit of help. And as always, I'm going to recommend that you watch this on your computer or your phone so that way you can follow along and take notes on your iPad. If you were in class today, we did a virtual lab online that relates to Charles' Law and Boyle's Law. If you are absent, you can go onto the Moodle page and complete this lab online on your own. On Moodle, it is called the Gas Laws Virtual Lab. One thing to keep in mind when you are working with gas laws is everything has to be done in units of Kelvin. Kelvin is equal to degrees Celsius plus 273. The reason for this is 0 degrees Kelvin is what is considered absolute zero, and this is the coldest possible temperature or theoretical temperature that anything can ever reach. One of the first laws that we learn about is called Boyle's Law. So Boyle's Law assumes that temperature and moles remain constant and that volume varies inversely with pressure. And what inversely means is that as, say, volume increases, pressure is going to decrease, or vice versa. As pressure increases, volume decreases. The equation that Boyle came up with for this is that pressure 1 times volume 1 equals pressure 2 times volume 2. And you can think of these as being an initial and a final pressure and volume. Good example of this is if you think of it like a balloon. If you take a balloon and you squeeze it, you're changing the volume, you're decreasing the volume of it, and inside the pressure of that is increasing because the molecules inside of the balloon are now hitting the walls of the container more and more and more because they don't have as far to travel to hit the walls of the container. And so as you keep squeezing that balloon, eventually the pressure becomes too great for the balloon to handle and the balloon pops. And now we will talk about what's called Charles' Law. So Charles' Law assumes that pressure and moles, again moles meaning just the molecules inside of something, as long as pressure and moles are constant, volume varies directly with temperature. One thing to keep in mind is that temperature is the independent variable and volume is dependent. What that means is that just because volume changes does not mean that temperature changes. However, as temperature increases, volume of something is going to increase. Or as temperature decreases, volume is going to decrease. But just because volume goes down does not mean temperature changes. Or as volume goes up does not mean temperature changes. Temperature has to change and that will affect volume. One way you can think about this is your car tires in the winter. So when the winter time rolls around, the temperature goes down and a lot of times you'll notice that the volume inside of your tires goes down and you have to add in more air. That, when you're adding in more air, means you are increasing the number of moles. You're putting more air molecules in there to increase the volume and the pressure. But as the temperature cools down, the volume of your tires shrinks. The third law that we're going to learn about is gay-Lussac's law. Gay-Lussac assumes that volume now and moles are constant and pressure varies directly with temperature. So as one increases or decreases, so does the other. A good example of this is you think of it like an unopened can of soup. If you were to place that can of soup directly on the stove, well, its volume's not going to increase. You know, a can has a pretty set volume. It can't increase or decrease without rupturing. It's just going to keep that same volume. So the volume is held constant like we talked about, but as you increase that temperature, again, temperature has to be the independent variable. As you increase that temperature, pressure is going to build up in the can because the molecules are going to be moving faster and faster and faster, causing more collisions with the wall of the can, which increases the pressure, and eventually, if that gets hot enough, that pressure is going to build up so much that the can ruptures. So as you increase temperature, pressure is going to increase as well. And now, to make our lives easy, we just take all of these laws and combine them together. This combined gas law now just takes all three of those laws that we learned about and combines them into one. So in Boyle's law, you'll notice we have P1V1 equals P2V2, so pressure and volume are on top. Charles' law has V1T1 equals V2T2, so again, volume on top, temperature on bottom, volume on top, temperature on bottom. In gay-lussac's, pressure is still on top, temperature is on bottom, and so it turns out we can combine all of them into this one simple equation of P1V1 divided by T1 equals P2V2 divided by T2. You'll also notice in here that we still do not have N, or our variable N, which stands for moles. So with this equation, we are still assuming that our number of moles, or our number of particles, in the equation, or from start to finish, is the same. Another key point of the combined gas law is that, let's say we're solving a problem, and we're pretending that temperature doesn't change. Well, all we have to do then is ignore temperature. Since temperature doesn't change from start to finish, we can just cross one out and say P1V1 equals P2V2. Or, if, say, volume doesn't change, and that would be an example like with the soup can. Well, if volume doesn't change, we just cross that out from the equation that we're going to use, and we're just going to say P1 over T1 equals P2 over T2. And you will see this in the upcoming slides as we start to solve for some of these problems. When solving any problems, please make sure to remember this equation. This is going to be one of our key equations for the entire unit, and starting tomorrow we will actually introduce this value of N. Alright, so here's our first example problem. I pump my bike tires to have a pressure of 70 psi on a typical summer day of 308 Kelvin. What is the pressure in the winter when the temperature has cooled to 273 Kelvin? First thing I always want to do is I actually like to look through and be like, alright, well, which variable is the same in both cases? So we talk about pressure, we talk about temperature. It doesn't talk about volume at all. So what I'm actually going to do is using my combined gas law, and this is just much easier than trying to figure out, alright, do I use Boyle's law, Charles' law, gay-lussac's law? I'm just going to start with the combined gas law every time, and then cross out whichever variable doesn't change. And since here we're not talking about volume changing, or it doesn't provide any volume changing, I'm just going to use the equation P1 over T1 equals P2 over T2. The first thing we want to do in any problem is define our variables. So it starts off by telling us, well, when I have a pressure of 70 psi at 300 Kelvin, I'm just going to say those are my starting values. So we're going to say P1 equals 70 psi, T1 equals 308 Kelvin. Again, pressure, we can use any sort of units. The units just have to be the same from beginning to end. Temperature has to be in terms of Kelvin. We cannot use degrees Celsius. So we start with P1 equals 70 psi, T1 equals 308 Kelvin, and then we put in our next variables. P2, well, we don't know. That's what it's asking us to solve for, is our pressure at the end, our pressure at 273 Kelvin. So now we're going to take and we plug those into our equation. So P1 equals 70 psi, T1 equals 308 Kelvin is equal to P2 over 273 Kelvin. And then using our above average algebra skills, we want to solve for P2. So multiply both sides by 273 Kelvin, multiply by 273 Kelvin. And a couple things to note, well, these are going to cancel out. And on the left side here, Kelvin cancels out, Kelvin cancels out, and we are left with our units of psi. So we take our 273 times 70 divided by 308, and we get an answer equal to 62.05, and our units are psi. But please remember to always use your sig figs. So we have 3 sig figs in each of these, so we will have 3 sig figs in our answer. When we're dealing with multiplication or division, our sig figs always follow our rule of the least number of sig figs in any of our given variables. So in this case, we are going to change this from 62.0 to 62.05 to 62.0 psi. Another thing I would always recommend with any of these problems is to reason through and think if your answer makes sense. Since we know that our temperature decreased, and if we think about like what happens to our car tires in winter, as the temperature goes down, our pressure inside of the tires goes down. Well, in this problem, our temperature decreased, so therefore our pressure should decrease as well. And if we look at this, our pressure goes from 70 psi to 62 psi. So therefore, our answer makes sense. In the second example problem, a hot air balloon rises because the hot air inside is less dense than the cooler air outside of the balloon. Now it is asking us to calculate the volume of air that will occupy a balloon at 43 degrees Celsius, which is also known as 316 Kelvin, if it occupies 2.5 liters at an outside temperature of 295 Kelvin. This problem is trying to confuse you a little bit and giving you the option to use degrees Celsius. Please remember, we do not use degrees Celsius when we are solving using our gas laws. So first thing we should do is go through and define our variables. Well, it's having us calculate the volume of air a balloon will occupy at 316 Kelvin. So we need to solve for our volume at 316 Kelvin. So we're just going to say, and again, it doesn't matter what's 1 and what's 2, it's going to give you the same answer. So volume 1, we don't know. Temperature 1 is 316 Kelvin. And then we assign our V2 T2 because, again, remember, it's not giving us pressure at all, so therefore we're just going to cross pressure out of our equation, and we're going to use the equation V1 over T1 equals V2 over T2. And now we go through and assign our second variables. So volume 2 equals 2.5 liters, T2 equals 295 Kelvin. And we plug those into our equation. And in this case, we are going to be solving for V1. So we are going to multiply both sides by 316 Kelvin. Multiply by 316 Kelvin. Because because whatever we do, if we want to cancel something out on bottom, we need to put on top. So our 316 Kelvin cancels out on that side. Kelvin units cancel out here. And we take 2.5 times 316 divided by 295. And that will give us an answer equal to 2.6. And we will say 2.68 liters because the final units we are left over with is liters. And again, think through our answer. You'll notice that our temperature went from 295 to 316. So as our temperature increased, what happens to our volume? Well, generally our volume increases as well. So it makes sense that our answer went from 2.50 liters to 2.68 liters. And again, this answer should have 3 sig figs because all of the numbers we were provided had 3 sig figs as well. Now that you have seen a few example problems, I'm going to ask that you please try solving this one on your own. So please take a couple minutes and try and do this one. Okay, now that you have tried to solve this problem on your own, let's go through and figure this out. So, a gas at 110 kilopascals and 30 degrees Celsius, again we don't want to use Celsius, so I'm just going to go ahead and cross that off since it gives me the temperature in Kelvin, fills a flexible container, and the reason it says flexible is it just means that the volume can change. Unlike when we talked about that can of soup example, where the volume is not going to change, this is more like a balloon, where its container, it's a flexible container, its volume can change. And so, if we look at this, alright, we have a pressure of 110 kilopascals, temperature of 303 Kelvin, and a volume of 2,050 milliliters. Now we're saying if the temperature has increased to 353 Kelvin and the pressure is increased to 404 kilopascals, what is the new volume? Well, this is the first time we have actually been provided a pressure, volume, and temperature. So in this case, we can't cross off any of our variables because they're all changing from one side to the next. And now we can go through and start figuring out, well, what variables are what. So I'm going to assume, or assign, pressure 1 is 110 kilopascals, temperature 1 is 303 Kelvin, and volume 1 is 2050 milliliters. My P2 is going to be 440 kilopascals, temperature 2 is 353 Kelvin, and my volume 2 we have to solve for. That's what the question wants to know. So if we go through and start solving this and plug in our variables, we have our P1, V1, and T1 is equal to our P2, and I'm sorry, this should not say T2 up top here, this should say V2. That's what we're solving for, and then we have our T2 on the bottom. So if we start solving for this one, well, to get this 353 Kelvin on bottom to cancel out, I need to put that on top. It's just like solving dimensional analysis problems. And to get this 440 kilopascals on top to cancel out, we need to divide by 440 kilopascals. And so now we can go through. This cancels out with this cancels out with this, and we need to do the same thing to the other side. So we multiply by 353 Kelvin over 440 kilopascals. I'm sorry, that should be a 0 there. And now we can cancel out our units on this side. Kelvin cancels out with Kelvin, kilopascals cancel with kilopascals, and we are left with units of milliliters. And if we go through and plug this into our calculator, we see that V2 is going to be equal to 650.27 milliliters. And as always, we want to go through and double check our sig figs. And our sig figs, our pressure only has 2 there because this is a 0 with no decimal point. Temperature has 3, this one has 3. Again, there's a trailing 0 with no decimal, so that is not significant. 440 kilopascals has 2. Temperature has 3, so in this case we are going to put our answer to 2 sig figs. And if we do this, we are going to say that our volume 2 is equal to 650 milliliters. Because again, that 0 does not have a decimal point, so 650 is going to be our 2 sig fig answer. As always, please try this problem before you watch the video tutorial for it. Okay, now that you have tried this problem out on your own, what is the pressure of a fixed volume? So again, volume cannot change, and therefore we can automatically go through and be like, alright, volume is not going to be used in this problem. So what is the pressure of a fixed volume of gas at 30 degrees Celsius, all known as 303 Kelvin, if it has a pressure of 1.1 atm at 280 Kelvin? I'm just going to cancel my degrees Celsius since we won't be using those. And we plug in our variables. P1 is equal to 1.1 atm at our temperature of 288 Kelvin, and then it wants to know what is the pressure at a temperature of 303 Kelvin. And so we go through and plug in our variables here, and we have our pressure 1 over our temperature 1 is equal to our pressure 2, what we're solving for, divided by our temperature 2. So we need to get pressure 2 by itself. To do this, we're going to multiply both sides by 303 Kelvin. These are going to cancel each other out. We're going to multiply the other side then by 303 Kelvin. Our units of Kelvin cancel out, and we see we are left with units of atm, which is good because atms are a unit of pressure. And when we plug this into our calculator, we get that P2. And I should say when we plug 303 times 1.11 divided by 288, we get an answer equal to 1.167 atms. But again, we want to watch our sig figs, and each of these answers, this is 3 sig figs, 3 sig figs, and 3 sig figs. So therefore our answer should also have 3 significant figures, and we get an answer of 1.16 atms.